What lies at the heart of every atom? The answer reveals a world of forces, particles, and transformations that shape everything around us. In this journey, we'll explore atomic structure, the fundamental forces that govern matter, and the fascinating processes of radioactive decay. After our opening, let's preview the journey ahead. We'll start with the building blocks of matter, then uncover the forces that hold atoms together, explore how nuclei change and decay, and finally see how radionuclides are produced. Atoms are made of fundamental particles, each with unique properties and roles. In this topic, we'll break down the basic constituents of matter and the language scientists use to describe them. Here's how the basic constituents of matter work. Nucleons and electrons form the foundation of atomic structure. Nucleons are the protons and neutrons found in the nucleus of an atom. Electrons are negatively charged particles that orbit the nucleus. Notice how atomic nomenclature helps us identify and compare different elements and isotopes. This table shows the key attributes used in scientific notation. The isotope iodine-131 has a mass number of 131, atomic number 53, and neutron number 78. The isotope iodine-125 has a mass number of 125, atomic number 53, and neutron number 72. The isotope iodine-127 has a mass number of 127, atomic number 53, and neutron number 74. Here's how scientists classify atoms. Isotopes, isobars, and isotones each highlight a different relationship between atomic numbers and neutron counts. Isotopes have the same number of protons but different numbers of neutrons, as seen in examples like iodine-125, iodine-127, and iodine-131. Isobars are atoms with the same mass number but belong to different elements. Isotones have the same neutron number but are different elements such as iodine-131, xenon-132, and cesium-133. Here's how nuclides and isomers are defined. These terms help us describe the unique states and identities of atomic nuclei. A nuclide is a specific nuclear species defined by a fixed number of protons and neutrons. Isomers are two nuclides, where one is a metastable state of the other, such as technetium-99 and technetium-99. Atoms are held together and shaped by fundamental forces. In this topic, we'll examine the four forces that determine the fate of particles inside the nucleus. Notice how the four fundamental forces differ in strength, range, and mediating particles. This table reveals the unique roles each force plays. The nuclear strong force has a relative strength of 1, acts over a short range of 10 to the power of -15 meters, and is mediated by gluons. The electromagnetic force has a relative strength of 10 to the power of -2, operates over an infinite range, and is mediated by photons. The nuclear weak force has a relative strength of 10 to the power of -13, acts over a short range of 10 to the power of -17 meters, and is mediated by gauge bosons. The gravitational force has a relative strength of 10 to the power of -39, operates over an infinite range, and is theoretically mediated by gravitons. Here's how the strong force shapes the nucleus. It counteracts repulsion, drives complex nucleon motion, and creates stable ground states. The strong force counteracts the repulsive electric forces and holds the nucleus together. Nucleons move about in the nucleus in a very complicated way under the influence of these forces. The ground state is the most stable arrangement of nucleons in the nucleus. Here's how unstable nuclear arrangements are classified. Excited and metastable states differ by their lifetimes and stability. Excited states have lifetimes less than 10 to the power of -12 seconds, often denoted as AX star. Metastable states have lifetimes greater than 10 to the power of -12 seconds, represented as AMX. Not all nuclei are stable. In this topic, we'll explore the processes that drive nuclear decay, the types of emissions, and the energy released in these transformations. Here's how nuclei change. Different types of radioactive decay transform unstable nuclei into more stable forms, each with unique emissions. Alpha decay involves the emission of an alpha particle, as seen in the example where radium-226 decays to radon-222 plus an alpha particle. Beta- decay occurs when a neutron converts to a proton, producing an electron and a neutrino, as in molybdenum-99 decaying to technetium-99 meters. Beta plus decay happens when a proton converts to a neutron, producing a positron and a neutrino, as in gallium-68 decaying to zinc-68. Electron capture is when a proton absorbs an electron, as in iodine-123, capturing an electron to become tellurium-123. Isomeric transition is the shift from a metastable to a ground state, emitting a gamma ray, as seen in technetium-99 meters decaying to technetium-99. Let's trace the chain of events in a typical radioactive decay process, from parent nucleus to stable daughter. The process begins with an unstable nucleus, which is the starting point for decay. A decay event occurs, leading to the emission of particles or energy. The daughter nucleus is formed, which may be more stable or undergo further decay. The daughter nucleus may end up in a ground or excited state, completing the sequence. Here's how alpha decay works. It's prevalent in heavy elements, produces short-range particles, and has limited imaging applications. Alpha decay is common among heavy elements at the end of the periodic table. Alpha particles have a very short range, traveling about 0.03 millimeters in body tissues. Due to their short range, alpha particles have limited use in medical imaging. Here's how beta decay unfolds. It produces short-range particles, maintains mass number, and can lead to gamma emission. Beta particles have a short range in biological tissue. In beta decay, the parent and daughter nuclei are isobars, meaning they share the same mass number. Excited states resulting from beta decay often decay further by emitting gamma rays. Here's how radioactive decay is quantified. The decay constant, exponential law, and half-life formula all describe the process mathematically. The physical decay constant, lambda sub pH, defines the rate at which radioactive decay occurs. Radioactive decay follows an exponential law, where the number of nuclei at time t equals the initial number times the exponential of minus lambda sub pH times t. The half-life is calculated as the natural log of 2 divided by lambda sub pH. Here's how effective half-life is determined. It combines physical and biological decay constants to reflect real-world elimination. Physical decay is governed by lambda sub pH, which comes from nuclear properties. Biological decay is described by lambda sub b, representing biological elimination. The effective decay constant lambda sub e is the sum of lambda sub pH and lambda sub b, and the effective half-life Te is calculated as Tph times Tb divided by Tph plus Tb. Radionuclides are essential for research and medical applications. In this topic, we'll explore how these unstable nuclei are produced in reactors and cyclotrons. Here's how radionuclides are produced. Nuclear fission reactors and cyclotrons each use different methods to create unstable nuclei. Nuclear fission reactors produce radionuclides by adding neutrons to target nuclei, making them unstable. Cyclotrons accelerate positively charged particles, such as protons, to impact targets and create radionuclides. Here's how decay pathways differ. Reactor-produced radionuclides often undergo beta- decay, while cyclotron-produced ones favor beta-plus decay, or electron capture. Beta- decay is common in radionuclides produced by nuclear reactors. Radionuclides produced by cyclotrons generally decay by beta-plus decay, or electron capture. Here's how nuclear fission works. Uranium absorbs a neutron, splits, and produces a chain of decay leading to stable elements. Uranium fission involves uranium-235 absorbing a neutron to become uranium-236 which then splits into barium-144, krypton-89, and 3 neutrons. The decay chain is a series of transformations that eventually lead to stable products. At the heart of every atom, forces and transformations shape the universe. Understanding these processes reveals the hidden dynamics of matter. From atomic structure to the forces that bind and the decay that transforms, the story of atoms is ongoing. The journey of discovery continues, revealing new insights with every breakthrough.